Okay. Okay. So, can you all see my screen? You're all good? All right. So I have here the Haskell Coffee breakdown. So we did week 1 last week. Everybody hopefully got GHCI and GHC on their computer or using something like REPL.it. And the idea for last week was make sure you have some way to use Haskell. The REPLs are good, but we're going to really this week, starting this week, we're going to be using files, and REPL.it allows you to write files too. So it's a fine substitute if you can't get Haskell running on your computer. If you didn't come last week and you want to figure out how to get all this stuff running on your computer, then make sure you take a look at last week's video. You could even sign out here and go watch that video on our YouTube. That's in the chat on the Discord, where you can access the previous videos, and then you can come back and watch this video after we're done today. It takes a few hours for us to be able to put it back up online because of YouTube, and processing large videos takes forever. But it'll probably be within a couple of days that we are able to get it uploaded and everything. So for this week, the title was maybe you like Ethiopian beans, maybe you like Guatemalan beans. We're talking about sort of new types, and we're really bringing in the idea of what is a type. And as you know, Haskell is what they call a strongly typed language. Everything has types, from functions to individual types of things. Everything is typed. Even the greater than or less than signs are actually types of things. And so Haskell is also what they call a functional programming language. So the majority of things, even like the plus sign and everything that is similar to it, is a function, right? They might be infix functions, they might be postfix functions, they might be prefix functions, they might be all sorts of things, but they have different types of functions, and basically everything in Haskell is a function. So we're actually going to bring up functions this week, even though we're going to talk really more about functions in the next couple of weeks after that. But really, you need to know what a function is in order to do anything in Haskell. And so we'll talk about functions pretty early on today, and we'll get you started writing them right away. All right, so let's take a look. So here we are, Haskell and Coffee, week 2. We're talking about types, and we're going to talk about palindromes. Not that palindromes are actually a thing in Haskell, but they're going to be an exercise that we do. We're going to do a couple of exercises before palindromes, and then we'll get to palindromes. And we have our little cup of coffee down there. So what coffee are we drinking today? Nori already said he's got some chaga infused coffee. Anybody else have any interesting coffee? I've got a coffee drink, not a particular coffee, from my local coffee shop that does an ube coffee or espresso with ube syrup and some oat milk. Anyone else have anything interesting going on? I think you can unmute yourself, right? Are you able to? Maybe.
I'm having some truffled Arabic coffee today.
truffle coffees.
Yeah.
Let me see. Maybe people can't unmute themselves. All right, you can share it in your chat if you can. Oh, so we've got some Kenyan coffee. We've got some cappuccino with chocolate. All right, that looks good. That looks good. Somebody's Matthias is ordering things for the Chaga and Lion's Mane coffee. Okay, people are in bars or coffee shops, and that's always a great place to get lots of different coffee. Ooh, awesome coffee from the Awesome Coffee Club. Okay. All right.
I think we all need to note that Victor is trying to fake being in a coffee shop with that virtual background. Just needs to be pointed out.
Yeah, it's fake. I wish this background was real.
All right. As Matthias said, his Awesome Coffee Club donates 100% of profit to charity. So if that's something that definitely interests you, that may be my next shop for coffee then. All right. Okay, so let's go on. So we're gonna start. I told you Haskell's strongly typed. We got to talk about types. And what are types of things? Usually they're categories of things, right? And one major thing that all programming languages have and all elementary schools have is this sort of idea of types of numbers. Generally, this is the easiest intro into types of things. And there are types of numbers like natural numbers, like the counting numbers. And and in the counting numbers, you have a close relative, right, which is the whole numbers. And then there are integers, which hold on to all of those values from natural, whole, and the negative numbers. And then inside of rational numbers, you have all of those other numbers. If you divide them by 1, right? 0 divided by 1, 1 divided by 1, -3 divided by 1, right? You get rational numbers. Or you might have 1/2, -1/3, 1/4, -1/5, things like that. All rational numbers are integers where they are a fraction of p divided by q, right? Where p is an integer and q is an integer and q is non-zero, right? So you might say, okay, well, didn't you just define the next one? Didn't you define whole numbers by saying the natural numbers plus 0? And didn't you define integers by saying, oh yeah, they're the whole numbers and they're negatives, right? And didn't you say rational numbers are p divided by q, where p and q are integers? Yep, I did, right? Because natural numbers are a subset of whole numbers, and whole numbers themselves are a subset of integers, and integers, are a subset of rational numbers. And so there are there's this idea that there's two sort of major sets of numbers, right? The ones that the number theorists like, the rational numbers, right? And then you have some irrational numbers, which are made up of like transcendentals and algebraic irrational numbers. And you might have e to the A, where A is some algebraic irrational number, e to pi, where pi is, another irrational number, phi, you could have the square roots, your cosines, sines, sinh, tanh, all those functions create numbers that are irrational, right? But for the most part, computers don't really like irrational numbers. There are ways to store irrational numbers, but they're not actually storing the numbers themselves. They're storing the process of how you get to those numbers. Whereas on the rational side, they're actually storing some fixed representation of what those numbers are. And so you could calculate those numbers. So like rational numbers, you have two integers, so it just stores the integer values, right? And then the process of how to divide them, sure, but they're simple. Whereas the irrational numbers are less simple, right? And so we'll find out in a second what. In Haskell, you might call the ones on the left the basic types of numbers, and the ones on the right, usually you need some other package or some subset of some other data type to be able to look at what these irrational numbers are. And so we're really going to be mostly talking about what are the number theorists' favorite numbers. And so you would say, well, what are the types of numbers? And so when we say of numbers, we're talking about the categories, right? And so the reason they're sharing similarities, and the reason we use sort of like a Venn diagram that's got subsets of numbers, is they all share some similarity. And the thing that they share is the way that they're operated on, right? You can say some number is greater than some other number, or you could say some number minus some other number is another number, or some number plus some number is another number, or some number times a number is another number. However, when we get to division, division is a little funky because computers have different ways of dealing with division than we might normally have. And so we'll talk about that in a second. But in Haskell, all these numbers fall under the type class of num. And so that's rational, integer, and floating point and double. We'll talk about those in a second. So what are the types of numbers that are in there? We've got the natural, the integer, or the int. There are two competing integer types. Actually there's three, but we'll talk about the two basic ones, int and integer. And then there's rational, and close cousins, or parts of the same ideas of rational, are the floats and the doubles. In floating point arithmetic, they're not categorized as P divided by Q. If floats and doubles are not categorized as P divided by Q, like you might do in normal math. They're calculated in a slightly different way with a significand or a mantissa and an exponent. And the way that they chop up the bit patterns for those things changes how large a number or how significant the significand can be, and how big the exponent can be. And the difference between floats and doubles is the size of the number of bits that are allotted to each component. And so when you have a larger significand and a smaller exponent, you have different ranges or different precisions of values that you can have in the end. But so in theory, you could represent all floats and doubles as rationals. Because basically what a rational does is a p divided by q, or in Haskell representation, a p number sign q, which even though we're in most programming languages, we look at the number sign and we think, oh, modulo. Well, it is modulo arithmetic, but it's the actual division operation. And so let's talk about some types. Oh, well, actually, let me show my screen. And I'm going to hopefully move this one.
Hello.
Oops, why is that going to the wrong screen? Okay. All right, that should be big enough. So we're going to go into GHCI for a second, and we're going to take a look at nums. So if we look at what a num is, we can use this :I or :info, and we can say, what is num? And so num is a class, right? You'll see that it doesn't say data on the first two lines. So whereas if you look at integer, you'll see that integer is also a type. It has a type signature of integer, and it has the data definitions, whereas num didn't. Num is a constraint. We'll talk more about constraints before. And the things that a num has to share is plus, minus, and multiplication. Also negate, abs, signum, and from integer. So you can see that all things that are nums, so all things that are below a num, will share that capacity. So if you create a new type of number, say you're a number theorist and you have some new type of number that you want to define, then you have to make sure if it falls under num that it has that capacity, those plus, minus, and multiplication. The integer, you'll see, it has this instance num, which means it is an instance of the num type. And you might say, okay, so I think I have to import some of the stuff isn't always imported by default. But if we do, let's take a look at what the type of 3, the number 3 is. If we type that in here, we get that it is a num. So, and it returns this 3 is of type num, which has a constraint of type num. So say we said 33.333, we might expect, okay, that's probably also a num, but isn't it a floating point number or something like that? Well, if you don't specify something, it says it's a fractional number, which, and a fractional number is actually you might think of it as the way I defined what a real rational number is, where a number p divided by q, where p and q are integers and q is non-zero. Fractional handles that as a superclass or a super type. And you might say, well, if I make a really long one, won't it have to be like a double? Won't it? And no, it doesn't. It can still identify those as fractional numbers, not floats or not doubles. But then there is a way to convert the fractional numbers to rational numbers. And so you have this function called toRational that operates on fractional numbers or anything that can be converted into rational numbers. And you'll see this number down here, which is a huge integer divided by another huge integer, right? And you might say, well, what is the type of toRational of this number? And well, it's a rational number. That's what a rational number looks like in Haskell memory. Okay, so you might say, well, how do I take a number and how do I assign it or convert it into one of these other numbers? So say I wanted 3, but I want the counting number 3. I want it to be the natural number 3. I don't want it to have the properties of the integer. I want to be able to, sure, I want to be able to add them, but I want to, it won't understand subtracting down to past 0, right? So if we want to do, if we do : after the number, and then the type, we can get what type this 3 is. So this 3, instead of being this 3, where it's 3 num, where it has a constraint on 3 to be a num, here there's no constraint, but it's a natural number. And so once you add that : it becomes whatever it is. So if you tried integer, it would also be an integer. And say you wanted to do float, well, that's a float. And so you can have, oh, and I said there was not just integers, there was also int. So you can have int here, and they're just different storage representations of integers. So int and integer. Okay, so does everybody understand that so far? Okay, got some thumbs up. Any questions? If you have questions, raise your hand in the Zoom, and we'll stop and address those. Okay.
There is a question in the chat by.
Oh, there's also a, oh, was that your question?
That's me, yeah, same guy.
Okay, so
yeah, so
why
if you can show your terminal again, please.
Yeah,
why does it show twice? Yeah.
All right, so it is the result of that int of that type is 3 is int. If you just do the 3 int, that is in itself, that's the number 3. 3 : int is the number 3. And then the : afterwards is what it's telling you, the :t is telling you what that type was. So 3 : int is of type int. So does that make sense? So this is the number 3 : float, right? And then it's telling you a t of 3 : float is of type float. So it's just a, if you do colon, when we did the rational, the toRational, it only shows it once, right? And that's because the thing that we're giving in to rational, this 33.333 is actually fractional. So if we redid that one, t to rational 33.333 fractional. Oh, I think we need to make this something like okay. So if we do 33 : float, that's in here, right? That's what that number is. And to rational, the function on that input value is the output is rational. So the output of 3 : int is int, and the output of 3 : float is float. Make sense? Okay. All right, so there are lots of types in Haskell, and sure, they might be more complex, but there are also some other simple ones. There are some that are almost simpler than any of those integers or almost uncountable numbers, right? And one of them is the bool type class, and that has just two potential values, right? True or false. You can do a lot with true or false. Some of the hardest problems in the world, right? Those NP hard or the sometimes potentially non-parametric solution problems involve just Boolean circuits, just Boolean logic, right? And so the question is, so I mean, you can operate, you can create a computer with just Booleans, and so even though it's a very low hanging fruit in that it has just two possible values, either true or false, it's a very important class. And then we also have this char or char, depending on who you're talking to. In our Lux Inc., we just recently watched videos on New Haven, Connecticut pizza, in which they talk about char. So now the only way I can refer to char on pizza, and also in characters, is char. And so the bool and char classes, the bool has true or false, the char has all Unicode characters. And so you might say, okay, well, don't you usually need to specify a different encoding for Unicode? And there are times when you do need to do that, when you do a really expanded alphabet, but you might do like a scharfes in single quotes. And I'll tell you a little bit more about single quotes versus double quotes in a second. But the type of this in single quotes is a char, a single char. If you do type of A, the English alphabet A, you get also a char. But what about, so these are important, right? You use strings all the time in any programming language. You use Booleans all the time. You use numbers all the time, right? Those are pretty much like 90% of your programming is those three things, right? Oh yes, Matthias says it's not burned, it's charred. Yes. if you watch, we'll put a video in about New Haven, Connecticut pizza that tells you about the status of what char actually means on pizza. So what about these strings? Okay, so strings aren't exactly strings in Haskell. There is a string type, but generally, if you did t, and we're going to use double quotes, and say we'll use the A in Shopus S, in both enclosed in the quotes, what do you think is going to come back?
Set it before you switch to the aggregate device, or you need to adjust your audio applications that you're using.
Oh, I'm gonna mute everyone unless you have your hand up. Well, okay. Mute yourself unless you have your hand up. So the thing that gets returned. So CNC says straight up. Parake says array, and yes, there's no we don't call them arrays in here, but we get a square bracket char. Yes, Scott got it right, and Matthias got it. The char list, we call it, is the type of double quote a Shopus, right? And so if we try to if we try to write that like this, oops. What do you think would come out of it? Anybody have an idea?
Okay, and let's give this a little test.
Okay, so what comes out of it is the string. Okay, so the string representation of a list of the char. So yes, Russ got it, but really it is a square bracket char. So if we did what is the type of this, it tells you it puts it here again, but then it says this is a list of characters, right? And so if we did that's good enough. Okay, so all right. Let me go back to slides. All right, so char, pretty powerful. Oh yeah, so let me just quickly show you too the type for true, capital T true, and false. And if you do info bool to get the info about bool, you'll see it's got data, and the data definition is really simple. It's just false or true. The single pipe there between the false or true in the data definition means that it's one or the other, not both. Although if you did both, if you did and both, you would get right false, which is useful in computer logic, right? It also has instances that it's an instance of. You'll see EQ, ORD, enum, show, read, bounded, but you don't see num on there. And the reason is bool is not a descendant, right? Is not part of num. Even though sometimes in programming languages like JavaScript and other things, you might imply that it is a number, but it's really a bad thing here in Haskell. Okay, so we're going to talk a little bit about functions. So I'm just going to give you the outline of what like a super basic function is, with one input and one output, or at least one input type and one output type. You can have multiple inputs, so you might have multiple different input types, but you'll have one output type. So I put on here the dash dash, that's a single line comment. So it says this is a comment. And the first line says this is a function declaration or the type signature of the function, and it's required. So you'll have the function name, those two colons, which says this function is of type, right? And the thing that it's of type is an input type and then an output type, and they're separated by that that single arrow. So not equals greater than, but minus greater than, which is just the definition of how you separate the sequence of inputs and outputs, or inputs and outputs. And then, you have the function definition, which is also required. You might have so you'll have the function name again. And then you'll have some variable. Since we have one input type, we're going to have one input variable. And that input variable gets a name, and you bind it to that name by putting it after the function name, but before the equal sign. And then you do something with that bounded variable name of input type, and then you output something of output type. That output type can be IO if you're dealing with the if the input and output of the terminal, or you might have a Boolean saying, is that input type greater than 5 or less than, or greater than 5 than true, and if it's not, then false, or something. The output type always has to be that output type. And if you're running the Haskell language server, it'll give you hints. It'll also tell you when you've got errors before you even try and compile your code. So when I suggested installing the Haskell language server, it's for this reason, to make sure that your input types are the correct type and your output types are the correct type, and to give you little hints of maybe how you could write your code better, or find a solution to things. And so the idea behind being able to define a function or declare a function with type, and then have the definition use that type, is for something called, it's a type of polymorphism. So in OOP programming languages, you might have polymorphism like hierarchies of and descendants and things like that. Whereas here, the polymorphism is like type constrained polymorphism, where you have a function, and if you said the input type was integer for one of them and handled a certain method of doing something as an integer, but then you passed it rational, and you gave it the same function name, but you said the input type was rational, and you handled that a rational different way, whenever you called that function name with an integer, it would call the first function, and when you called that function name with a rational, it would it would call the second one. You might have seen this in other programming languages like C or C++, where you can overload a function or a symbol or something like that, right? You can do these things where it expects certain types and only will call that type when it's given a certain other type. And the reason it can do that is the power of types. Like, you can't really do it in JavaScript. You can't do it so much in Python, although now things are changing in Python. It's really important to remember the types that you're dealing with. So Haskell language server, very helpful in this, and definitely something that you'd want to work with using when your code is running and when you're compiling your code over and over again. It helps before you compile your code. Okay, so okay, so the other thing before we get to our first function is we're going to talk about case expressions. So expressions are like 5 + 3 or anything that evaluates to something. And case evaluates to whatever the result of whatever matching thing is. And so in case, you have a pattern and the result of what happens when a pattern matches. So you might have some variable a as a number, an integer. And then you might say case a of, and you give it some patterns that it might match. No, don't use this, don't copy this one down, because this is actually not a complete case statement. We'll look at that, or case expression case statement in a minute. But what we're doing here is we're giving it patterns. So all of these 3, 4, and 5 can be interpreted as integers. And so a is an integer. If a matches 3, then it's 3. If a matches 4, then it's 4. If a matches 5, then it's 5. And since we set a to 5, it would, if we had a complete case statement here, it would evaluate to its 5. And we'll show that in a second. But here is a coffee-related case statement. Here's our first coffee-related case. So what can you do with a list of chars? So we might have this function, origin of coffee, and it takes an array of chars, or a list of chars, and the output type is a list of chars. And you'll see on the left side, the patterns of the case are strings rather than, say, a list of chars. And the right side is also strings rather than a list of chars, just for simplicity, right? The convenience, the syntactic sugar, right? That allows you to represent the arrays of chars, or the lists of chars that way. And so we declare it, and then we define it. So we define origin of coffee, which is bound to a name variable. And then we do case name of, and I put some coffees from my favorite coffee roaster that might be related to a different region or a different country. And then we have this pattern at the end that is underscore. And the underscore pattern is the catch-all pattern. It's like default, but really what it is a wildcard. You might know them also as holes or other things. What they do is they say, if nothing else matches, match this. And so we might say, so if we enter into this function and we say Diego Campos, it should output a string that says Colombia. So let me go to the code. Hold on, let me. So let me load this. So I have here the function origin of coffee in this file called main.hs, but you can name it anything. And then I have here, you'll see the highlighting is because of the Haskell language server, and it shows the strings, right? In yellow here, and the single arrow here showing if it's Diego Campos pattern matched, then we get the result of Colombia. If it's Dumerso, then we have Ethiopia. If it's Alfonso Uriola, then it's Panama. And if it's anything else, then I don't know this coffee name. And so if we load this file and we run origin of coffee and we say, so there are a couple of ways to think about running a function. You can run it with just a space here. So you might say Diego Campos. So you might say, okay, well, that's correct, right? Give us back Colombia. And then what if we ran in parentheses, Dumerso, right? It gives us back Ethiopia. And there are some other options instead of the parentheses or instead of the space, right? We'll still get back the same value. But what if we enter something that doesn't exist, like Eli's new roasted coffee? It says, I don't know this coffee name, right? That's the expected result when it doesn't fit any of those other cases, and we have that catch-all. That's what it responds with. Okay, so I'm going to send out this file with this code in a little bit, but and there's going to be some space for you to write a function that we're going to talk about. There's also some stuff here in the main that uses the functions that we have here. So we say origin coffee, Diego Campos or Eli's coffee, and then we have the case statement inline, not written into a function here in the main as well. If you ever write a main function for something that needs main actually, and it has interactions with the terminal, having the type IO is necessary. We'll talk about that later. But anyway, so we don't need to use the main when we're dealing with the GHCI, but when you've got a compiled program that needs a starting point, you'll need the main. Anyway, so we'll talk about that more later. And so we've got this case that works. And what else could you use a case statement for? Oh, are the parents required in the case of? No. Can the case be evaluated with any type? Pretty much, I think so. It can be evaluated with any expression, right? So you could have x is less than 5 of whatever, or you can have anything that evaluates, right? So yeah, so it can be used basically with any type. As long as it evaluates, I think. I'm not exactly sure if it can be used for every single type, like types that you define. I think it might have to have equality, the EQ instance. So for that to work. We'll talk about that later, about like being able to implement the instance of values. So what else could a case be used for? Anybody have any ideas? Right, an if then, right? You could have basically use it like an if then else. So if you just had like 2 conditions or 3 conditions, then that's like an if, else if, then, right? What else? So some things you might use case statements for would be like a mapping from one value to another type. So say you have the letters A becomes a 1, B becomes a 2, and then you're mapping over a list that has that's a list of chars. Then you are going over each one and translating the list into numbers or something like that. Or you could have more complex values that are constructed from those outputs, those representations of the output. So what we're going to do is we're going to do something with a case statement. So you're each gonna, I'm going to send out the file, and then you're each going to make this cups of coffee per day function, and you're going to announce in the chat here. So yeah, it's like test case in some other languages. Yes. So we're going to announce here how many cups of coffee you have a day in chat. And then you're going to build a case statement with a few people's names. And the pattern as the pattern and not the years as result, but as the cups of coffee as result. And we're going to make a default catch-all pattern that says something for students that you didn't enter. So you might enter 42, like Matthias says, or you might enter 3. So what I'd like you to do is then direct message a classmate and have them give you a name. And if that name is one of the ones that you entered in your statement, it'll give back a number. And so I'd really encourage you to think about this, because the case results need to, the result needs to be of a certain type. And the function that we declared here has char list returns a char list, right? And you might say, well, if I'm giving a name and I'm giving a number, wouldn't the number and then say a catch-all that's not a number be a problem? And yeah, we've got somebody saying 1.25. So you have to think carefully, like, should this be a char array or a char list that's coming in, or should it be and should it be an output that's a char list, or should it be an output that's a double or fractional or something like that? Okay, yeah, or a float. Okay, so I'm going to send the file, but you can do this in your own directories or writing functions with GHCI, not exactly a fun thing, but it's possible, but it's kind of annoying. So I'd really recommend doing it in a file and then loading that file from the directory that you're running with GHCI. So let me send you this file so you can. So here we're going to say, write a function called cups of coffee per day. Think about the input name and the output cups per day, right? No. Okay. Okay, I'm gonna send this in files. Let me see if I can drag it. No, doesn't like dragging. I'll put it in the Discord chat. No, Nori, 40 ounces of coffee is not 1 cup. Okay, so I put the text file in the Discord chat, and I'll show you how to load the file from GHCI. So here I have a directory called Haskell Coffee, and I put that main HS file in there. If I start GHCI from that directory, all you have to do is :L, which is load, and then you do main, whatever the name of the file is. And that'll load the file, and then you might have cups of coffee per day available if you've written it. If you haven't written it yet, saved it, and then you're like, how do I reload it? You just do R or R main, oh, I think just R. Or you can do L main HS again, and it'll recompile it. I think the R may not recompile. So I would do the :L to recompile. Okay. All right. Yeah. So let's see. Well, let me see. Can you do tilde? Yeah, it looks like it accepts tilde. Yeah, it seems like it interprets those files. We'll talk about guards more later, with like sort of complex if statements with guards, or complex case statements with guards. Guards are a a continuation and prevention of yeah, we're going to get more into conditional stuff later. This is just sort of the first example of conditionals. Interesting. What happens if you do tilde? Oh, yeah. So start writing the function now. Robert, what if you type tilde numcups without the forward slash? Does it? It's interesting. You might have to rename. Well, I don't know if it cares about the name of the file. Rename the num-cups to numcups .hs. Let's see if that matters on the system, because I'm not sure if people are using WSL or if people are using different things, if it can't figure out what the path is, and maybe can't infer the type. Anybody having, let's see, trouble with this right now? And Robert seems to have some trouble with loading the file. CWD is actually PWD in Linux, so probably PWD, print working directory. That is a good question. I don't know. Let's see. You can just do CD, but let's see. Yeah, you can do exclamation mark, colon, exclamation mark, PWD, and that'll tell you the directory that it's in. Okay, so let's try and work through this together, and we'll write something here. Okay, so similar to this one, right? Oops. Didn't mean to import that. So we'll write cups of coffee per day. Name. It doesn't have to be name. I'm just using name for any good reason. Okay, so so Robert, almost. Yeah. You might not want integer in square brackets, because the value that you're getting out is not a list of integers, but a single integer. So here, let's do cups of coffee per day, char array or char list, and integer. And this might work, but we've seen a lot of floats out there. So I'm gonna make it a float. And then we say like Matthias had 42. Whoop, that is not what I wanted. And let's see. I'll copy what Robert had in his code. Let's see. Victor also had 42. And then Eli, okay, Eli had 1,000. I could have sworn I didn't even write one, but sure, I had 1,000. And then underscore, we had 0. So you'll see here that all these look like integers, but when we run this, we'll maybe see something else. So it'll say here, hey, oh, what did I do? I didn't do the case statement. That would help. So now it's saying nothing, but it sure reminded me that the case statement was necessary. Okay, and so then if we get back here and we do load main, then we do cups of coffee per day and we do Eli, we'll get 1,000.0, right? Because it has, if we do the type of cups of coffee per day of Eli, we get float, right? And so if we did cups of coffee per day, oh, let's say, let's have here, Nori had, he had 40 ounces, which I'm going to say is more than 4, but not quite 5 cups, because he's probably underestimating or overestimating his 40 ounces. So we're going to say 4.5. Okay. So we're going to say here, load that again. We're going to say Nori, right? And that'll still be a float. And if we do what its value is, it's 4.5. But if we changed this to integer, because maybe we didn't want the floats in there, it would be funny because it's saying here, hey, this is a fractional integer, and it's not, we're not expecting that type. We're expecting integer. So 42 works, 1,000 works, 0 works, but 4.5, So we'll round up for Nori then. And then we'll try that again. And we'll say cups of coffee per day for Nori, 5. Okay. So now it's giving me not 5.0 or 4.5, but it's giving me that 5. And if we get the type of that function call, then it's going to say integer. Okay, so that's a slightly different. Okay. All right, so Augusta, yes, that will give you an error. All right. So the Oshoma, the problem is the error, right? We will talk more about errors later, so we haven't really come to that situation yet. And there's one condition, Scott R. You have you have conditions, you have patterns of Jaime, Roberto, Robert, Matthias, but you don't have a catch-all. You don't have the underscore. So you'll probably want to add the underscore so that it doesn't warn you of those issues if you have them. Okay. Unknown coffee drinker species. That's funny though, Robert. I like that error. Oh, yep, Scott, you got that underscore in there. Yep. Okay. All right, looks good. So let's go on to the next thing. All right. So, okay. So we have the coffee per day, and now we'll talk a little bit about if then else. So if then else, just like in other programming language, says if some evaluated statement, then if that statement evaluates as true, do something, otherwise do something else, right? So if x is greater than 0, what is that? What do you think that evaluates to? Bool, right? Yep. So we've got bool values. So and we'll tell you why that evaluates to a bool in a second, and what x has to be in order for that to evaluate. So here x is an integer and 0 is an integer, or can be considered an integer, right? So greater than should mean bool true or false, right? And negate, we saw that when we did the type of num, that negate is one of those base functions that's available on num, not just integer, but all of num type class, right? So if we do negate x, we should get the negative, the inverse, the additive inverse, right, of x. And if it's not, we're going to do x minus 1, right? So if we imagine x as an integer, if x is greater than 0, that means 1 or greater, then we give it a negative. And if it's not, then we do x minus 1. So what are the domain and range of this? So the domain are all the integers, and the range is what? If we had to think of this as a math function. Oh. So x has to be an integer. Yes, Haskell will error if you try and give this function something that's not an integer. It does not like coercion as much as other languages do, like JavaScript will coerce your values into things that are definitely not what you expected. Right. Range, negative 0 to negative infinity. So almost negative infinity, but it's the range of integer. So integers several billion, right? So billions and billions. So we're pretty good for any number that we probably will enter. So at a glance, we're going to look at what constrained polymorphism is. So we talked about how if we gave the types, the colon integer, then we could tell the compiler, tell the program what what that value was, what type it was. If we give it num, which is a type class, then the type class will say, okay, you have some things like negate works, x is greater than 0 works, blah, 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 blah. Ooh, does it? Oh, I don't know. So if we try this, actually we'll get an error. And the reason is we constrained it to number. So A has to be a num. So it could be an integer. It could be a num without any type. It could be a float or whatever. But if X is just a num, then we get an error. And so I'll tell you how we can constrain that even more. And the reason is, so negate and x minus 1 are from num, but greater than comes from ord. And ord is another type class. And so the question was, does that equal greater than mean equal to and greater than? No. This this right here, where it says num a and then equal greater than, is called a type constraint. And what a type constraint means is that a, if you put these in parentheses up there, num a has to be a num. So if you tried to run this function with a being a string or something like that, a char array, it would error. And it would say, I can't do that because a is not a num. A is a char array. So better luck next time. Let's try again. Or, well, it will crash the function, crash the program. So we have to make sure that that a is also has an instance of ord, so that we can have that x is greater than 0. So instances are not exactly subclasses. They extend the functionality of that class, or they implement the functionality of that class. And we'll talk about that later. It's a little more in depth than where we're going to now. We're just looking at it like a brief overview. So that num a is not enough. We actually need ord a and num a for a to work in this function. And what are some examples of things that have ord a and num a? Well, if we look back at this one, if we do type of num, we'll see, oops, I don't mean type, I mean I of num. Then we get here num is an instance of num, right? The instances of num are word, integer, float, double. So let's take a look at integer. If we look at integer, says here integer, it has EQ, it implements ord. Hey, there's ord, right? So a type that would allow both ord and num a, oops, is integer. So you might have integer, float also works, all those other descendants that implement the ord and num will be able to function here in that less than 0. So let's talk a little bit about other things that have constraints. You might try and write something that has a declaration for the function that does, we call it likes A. So this prefers A or chooses some value that has A in it over the other value if the first value is A. So we have likes A and we have two arguments, M and N. And if lm A, so A in single quotes there, what type is A in the single quotes? Right, it's a char, capital C char. Remember your capitals here just in case. And then if lm M, so A and M are arguments to this function lm, then we choose M. If not, we choose N. So M and N. So since M and N are the return values, we'll have to look at what types those are as well, right? M can be returned or N can be returned. But what does lm A in single quotes M mean? Anyone have any idea? Oh, maybe I should do an example. So some people had some questions on the previous slide. Oops. Let's take this likes A, and we'll do it here. So likes A, and we'll say board. If I can type. Oh no. Less than 0, not likes A. What am I doing? Less than 0. Word A, num A, right? And we're saying then the input type has to be A and the output type has to be A. So you could say maybe the input has to be A and the output has to be bool or something. But here we're saying that the constraint input and the output are the same, are both number and ordinal, or are ordered, orderable. And so we have here, we'll define the function less than 0. And we'll give it some variable. We don't have to call it A. A is just a type that's being constrained. So whatever, we could call this number. And number has to be constrained by ord and num, meaning that it implements, it is instance that implements ord and num. And so we're giving A is the first argument and A is the result. So they both have to be ord and num. So if we have here less than number, so we say if number less or greater than 0, right? Then we do negate number. So in order to negate number, we need number to be a num. And in order for number greater than 0, for greater than to be a function that works, number has to implement the order type class or be an instance of that. And then we can negate it if it's greater than, else we'll do x minus 1, right? So, but it's saying here, hey, look at this redundant bracket. So this is a stylistic thing where it's telling me, hey, you don't actually need these parentheses, and that's fine. We can take them off, right? Still, oh, I don't mean X, I mean number. Okay, so now it has no problems. It doesn't matter if we put those parentheses or not. We could have left them in, it would still compile with those warnings in there. But it's better if we don't. So we'll leave them. And then we do less than 0. So say we try and give it now 0 as a float. We get -1, right? As a float. It's coming out. So if we do type of that, we're getting a float out. And the reason is we're saying here A, and the return type has to be the same type. If we said bool here, this calculation wouldn't work. Here it would give us an error here. So negate number doesn't work with bool. Negate number doesn't result in bool. It results in the same type as whatever A was coming in with. So that's the reason why we leave it as A, is because negate number returns whatever type of number A was, or coerces it into something that is num and ord. Then number -1, it's also minus, which is in the number the num instance. So we did 0 float. We could also do 0 int, and that comes back with an int. And we could do 0 double. We could do 1,000 or 10,000 as a double, and it would still come out as a double. If we tried to do less than 0 of something that might have order, like a string has order, but it doesn't have num, what would happen? Ooh, we get an error. Says there's no instance where num, where this char list is actually constrained to a number. So we can't use it. We can't use this function with that value. And so it stops the function, right, and exits it. So we could take away this num and just keep order, but then negate and num -1 wouldn't work. And so you've really got to be thoughtful of what your types are and what the constraints are. So this constraint applies to one variable, even though it's got 2 types that it's constraining to. Okay, let me look, let's see if you got that. Okay, let's try this. Okay, so what happened when you did -3? Ooh, why is that a problem? So let's say this is integer. Ooh, doesn't work. Why? But if you put it in parentheses, it does. So what is that error talking about? So it's not the same error you got before, where it's like, hey, this number is not actually a num. The reason is the minus sign is a tricky sign and actually is a function. And when we put it in the parentheses, it says, oh, hey, there's nothing preceding it. So it's not actually a value that's being called on less than and minus and less than -3. You can also do the $ there, or you can do without the int if you do the $ saying that -3 would be in parentheses. So there are some options for how to call that function with that argument as a value. Okay. Okay. All right, so let's go back to the stuff we were working on. So what does, let's go back to this function, the likes a. What did lm single quote a m mean? So remember, these are two arguments to the function lm. Any idea? Throw it in the chat if you know. So element A, yeah. So element, it means it'll return a Boolean. A is an element of M, yes, a shoma. Yes, does it mean there is a type restriction or a type constraint on M? Yes. And what things have elements? Lists. Yeah, so M should be a list of something, and A is what? Char. We've identified that a couple of times. So element is element A in list M. And what type of list would have the element single quote A? Yes, Robert got it. A character list. So if A is in a list of M, which is a list of characters, right? Then we'd know that this function, LMAM, would have a type signature where it would have, here, let me just write it here. So we would have LM, oops, that's not how you spell LM, would have type signature. The first argument would be char. The second argument would be char. Remember how I said that input might be multiple inputs? Well, here LM has two inputs. So char and then a single arrow and then char single arrow, and then the output. So always the last one that has an arrow to it is the output. And what is the output of LM single quote AM? Bool. Yes. So we would have bool. So this would be what LM would have for this particular instance. When it's used on M, that's a list of chars, and A, which is a char, then LM would say bool if A is in M. So if A is in M, so we know M is a list of chars and N is a char, or we know that M is a list of chars, then what type is N? Robert needs coffee. I need coffee. False. Okay, well, it's a bool. False. No. The N is actually, so if you look here, the return is either M or n. And M, we know here, is a list of chars. So N is probably also a list of chars. So, so what is the type declaration signature of this likes A? So let's go here and we'll type it. So this won't do anything. Likes A. So we have here two elements that are the arguments. And so what are those? Those are char and char. And then what is the output? The output is either is char list M or char list N. So they are both char lists, right? So that would be likes A, would be char, single arrow, char, single arrow, char, right? And so that would be that definition, right? And so we will want to take a look at what lists are. So we're going to do a little playing around with lists. And in your GHCI, I'd like you to type :info or :I, and then open and close square brackets and see what it tells you. And what do you think that means? Basically, yes, you can have a list of any type that's accepted in Haskell, and except there's some instances there that are pretty substantial, and so we have there's this applicative square bracket and equal A. So you can have the equivalence of two lists. You can have the ordering of a list of A's. You can show A. Show is frequently defined as the printed version of whatever data or type that you have there. Monad fail. Is there an ointment? Yes, Robert. I'm not sure if there is. Hopefully we don't get the fails, but we will fail eventually. Okay, so how do we construct a list? We saw that before with the A and sharpest S, and we might have a list of integers or something. And we might say integer, right? So that's 0, 1, 2, 3. If we do the type of that without the integer, what are we going to get back? Anybody remember? What types are the 0, 1, 2, 3? Almost. They're going to be nums. And so if we look up here, because we gave it an integer type for the list, it's going to give us integer back. But because it's we didn't give it that type with the 0, 1, 2, 3, it's just going to give us back num. Okay, so what can we do with lists? We can construct lists. So let's say this colon here, single colon, is often used as a constructor. So if we do that, what do we think this is going to provide? So 0, 1, 2, 3, square bracket. Yep, it creates the list of numbers, right? The list of nums. And the reason this works is because this colon is the constructor. It constructs a list and it'll go from right to left here. So it'll put 3 and 2 and 1 and 0 onto the list. And so we get that list back. So when you const anything and a list, it puts it in the list. So if we do oops, this, what do we expect to get out? Yeah. So why doesn't it do when we do 0, 1, 2, 3 with the colons and the square bracket, why doesn't it return 3, 2, 1, 0? Dennis is probably right, except we get a string back. But it is the same, so that single quoted ABC we get back the double quoted ABC. Oops. All right. All right, so let's talk a little bit about palindromes. So if we have, so one of the most famous palindromes, well, okay, one of the most famous is race car. Madam, I'm Adam, that's another one, right? Except we'll talk a little bit about Madam, I'm Adam in a second. It's a great phrase, right? But it's got some interesting pieces that we'd have to strip out if we really wanted to know that it's a palindrome, right? The single quote, capital letters, spaces, yeah, we'd have to remove a bunch of things, all right, just to make sure that it was a palindrome. And so we'll do that. That's actually going to be our homework. The bonus question on homework is going to be if you can find a palindrome that has the word coffee or the word bean in it, then you get like 100 extra points in this class then. Okay. So what makes up a palindrome? A palindrome is if you can read it from the left and right and it is the same set of words or word. One that people like a lot is taco cat. So all the taco cats that are out there, they're really edible and cats at the same time. Then what we want with any of these is to figure out how we can check if they're the same. And what's a way that you can check if a palindrome is the same, forward and backwards? Yes, palindrome coffee. I looked that up too, Scott. Yeah. Is there a reverse function? So let's take a look. So is there a reverse function? There is. And hey, it reversed that that thing, that taco cat. But if we try Madam, I'm Adam in there, it looks a little funky, right? It definitely does not look like Madam, my Madam, even though it was reversed. So we're going to have to do things like remove elements from that. So right now, for this first class, we're not going to worry about the ones that have punctuation or single quotes or spaces in them. We're just going to worry about race car, taco cat, and was there another one that someone had? Ada. Ada is a palindrome, right? Yeah, so we've got 3 in there. So what I'd like you to do is write a function that reverses a string, and it should take an input that's a string and return a string, and then figure out, oh, actually I should write here. I didn't write this correctly. So we're going to write a function that takes a string, reverses a string. Actually, let's say this. Write a function that checks if a word is a palindrome. The function to take a string as its input and return, let's say we're going to return a Boolean. So bool. And then figure out how to test that in the main of your function. So down here in the main, where I've tested the origin coffee and the this case statement down here, you can remove them or whatever, and then you can put in your tests of your function. And let's call this function, is this a palindrome? And you have to figure out the input and the output. And remember, there's just one input and there's just one output. So how many arrows are you going to have here? You're going to have some input type, and how many, and are you going to have another input type or just one input type? Oh, ooh. Thank you for the notes. Is this a palindrome? So one input, one arrow, and one output. Okay, so output type. So you'll have to figure out what those are. And remember, we said takes a string and returns a Boolean. And then write the function here. Then write the function. Okay, so I'm going to send this out to you. And this is the stuff you're going to fill in. And we'll talk about it at the beginning when we talk about the coffees next week. So what are some ideas that you might have about how to test if something is a palindrome? Anybody have ideas? Single head split into 2, that's possible. So head might be an advanced version of this. Dennis has a good idea there, checking, comparing with the reversed one, right? And so how do you compare strings? How do you compare anything in any programming language? Is 0 equals, not 3 equals, I'm not writing JavaScript, 1, No, false. Is 0 equal 2? No. Is 0 equal 0? True, right? So equals equals will work. Does it work on strings? A is equal B. False. But is A equal A? Yes, true. All right, so checking and comparing strings works. Okay, so you'll try that on yourself. I'm gonna resend the updated file, the main HS file, to the Discord. Make sure you get on the Discord. Okay, let me get the link to the Discord. Where is it? Okay. Oh, there. Victor has it. So, all right, I'm gonna stop sharing now, and we'll be back next week. Thank you all.
Thanks for your time, Oli. Nice talking to you. Yeah,
No problem.
thanks very much. See you next week.
See you next week. Remember, week 3, we're dealing with Haskell programs, non-empties, and sort of a real first Haskell, a coffee-based Haskell exercise that you'll do on your own. Okay, so which editor do I use in terminal? I use NeoVim. You can use regular Vim, NeoVim, VS Code. I'm sure one of the IDEA products works with Haskell. I'm pretty sure they've got one for everything. But VS Code is pretty easy and works with Haskell language server, so you can install that. Also, if you have GHC up, then like VS Code automatically like interacts with GHC up and installs the Haskell language server for you if you hadn't installed it. So that's also possible. So there will be a recording. So we did record this class. We will put it up on YouTube. And Matthias pointed out that some things about the case without a case. So you can like overload your functions, and you can instead of writing a case statement, you can just write overloaded function with lots of inputs to that function. So that totally works. Oh yeah, somebody put up Haskell IDEs. I had not looked at that. Yeah, Haskell language server, VS Code. There is an IntelliJ plugin for Haskell. I have never used Lexa. Vim, Emacs, Atom, probably a million other things. There's Sublime also. All right. Thank you, everyone. See you next week.
Bye-bye.
Bye.